In this video here, we're going to take a look at objects moving in vertical circles. Now, when an object moves in a vertical circle, it gains height as it follows its circular path. Now, if it gains height, then it must also gain gravitational potential energy, right? Which we often just abbreviate to GPE. So therefore, then using the work energy principle, it follows that it must lose kinetic energy, and its speed will not be constant. Now, what we can do here then is use vectors to understand motion in a vertical circle. So examples of motion in a vertical circle could include a Ferris wheel, for example. That's the whole point of this image here. Or a vertical circular loop of a roller coaster, right? So before we work through a practice question together here, let's just explore the concepts of objects moving in vertical circles in more detail. So to continue here, then we will let the unit vectors I and j be parallel to the x-axis and the y-axis respectively, and we'll also make use of this diagram here. Now, at time t, then the angle between the radius OP and the x-axis is theta, as we can see here then on our diagram, and the position vector of p is simply given as r. So r then, nice and straightforward here, is just simply r cos theta I plus r sin theta j. Nice and straightforward, right? Now, what we can do here is just differentiate this with respect to time t. And if we do that, then we obtain the following velocity vector. So v here is equal to the following. I won't bother reading out all of this here. As you can see, that's just a straightforward application here of calculus, right? So as we just said then, the velocity vector here is equal to the derivative here then of the position vector r, again, with respect to time t. And if we do that, then we obtain the following velocity vector. Now, if we just look at the directions of r and v here, we can see then that the lines representing them have the following gradients. So we get r sin theta over r cos theta and minus r cos theta over r sin theta respectively. So this here is for r, this position vector, and this here then is for the velocity vector. And hopefully what you can recognize here then is that if we take the product of these two gradients here, so r sin theta over r cos theta times by minus r cos theta over r sin theta, what's going to happen here then is this will just cancel with this will just cancel with this here, and all we get left with then is just minus 1, right? And what that means then is these two vectors here are perpendicular. And by the way, you can also just verify this here by using the scalar products. If you want to, feel free to do that as an exercise. It's not compulsory, but again, you might find that useful. And what this tells us here then is that the acceleration has two components. So one of magnitude r times theta dot squared directed towards the center of the circle, and one of magnitude r times theta double dot directed along the tangent to the circle. So to summarize here then, for the motion in a vertical circle of radius r, the components of the acceleration are either r times omega squared, or alternatively here, v squared over r towards the center of the circle. And in that case, then we obtain this relationship here. So r times theta double dot is equal to v dot along the tangent. And then just finally here, just note then that the force directed towards the center of the circle is perpendicular to the direction of motion of the particle. So what that means here then is it will just simply do no work, right? Now, if the only other force acting on the particle is gravity, then it follows that the sum of the kinetic energy and potential energy will be constant. And we're going to use this fact here throughout to solve many different problems, okay? And we'll see that later on, throughout this chapter as we work through different practice questions, okay? So we've just got one more slide here to finish with. So to conclude this introduction here, we do also need to understand then when an object will perform a complete circle. So as we can see here, right, as we work through questions on this topic, many of the questions will often ask you to consider whether or not an object will perform complete circles. Now, there are slight differences then between particles attached to strings and rods. So what we're going to do here then is just use the following conditions to determine whether particles moving in a vertical circle perform complete circles. So for the first point here, or the first condition, a particle attached to the end of a light rod will perform complete vertical circles if it has a speed that is strictly greater than 0 at the top of the circle. For the second point here, or the second condition, a small bead that is threaded onto a smooth circular wire will perform vertical circles if it has a speed, again, that is strictly greater than 0 at the top of the circle. So as you can see then, almost identical here to the first point or the first condition. And then for the very last point here, or the very last condition, a particle that's attached to a light inextensible string will perform complete vertical circles if the tension in the string is strictly greater than 0 at the top of the circle. Now, what this means here then is that the speed of the particle when it reaches the top of the circle must be large enough to keep the string taut at the top of the circle. And hopefully that does seem quite intuitive. So to finish with here, that concludes this introduction, right? What I would say here is just please do make a note of these final 3 points, right? It's important that you do understand the difference here with each individual situation, okay? So as it says then, to finish with here, let's just work through a practice question together. So let's just have a go then at the one practice question here for objects moving in vertical circles. So as always then, let's just quickly read through the question here. So what we've got then is a particle here of mass 0.2 kg that is attached to one end A of a light rod AB of length 0.5 meters. Then told that the rod is free to rotate in a vertical plane about B, and the particle is held at rest with AB horizontal. The particle is then released, and what we want to do here is just calculate the following, right? So for the first part of this question here then, part A, what we want to find here then is the speed of the particle as it passes through the lowest point of the path. Now what we can see here then is that we don't have a diagram, right? And generally speaking, for questions such as this one here, a diagram really is quite helpful. So it doesn't matter if your art skills are as bad as mine, right? Just draw a quick diagram, don't be lazy. Like I said, it doesn't need to be a masterpiece here. So what do we have then? So what I've got here is basically the center of the circle. Okay, like this, we have a horizontal rod, AB. Okay, so it's going to look, say, something like this. And this point here will lie on the circumference of the circular path, right? I've done this maybe a little bit big. It's going to be quite a large circle, this, which by my art skills is not going to be pretty, but I'll give it a go. And draw a circle through this here. It's not great, but it'll do. It'll do. Clearly, this needs to be much larger. Let me just shorten this here and lower it a little bit, just to make it look a little bit neater, because that's shocking. I'll do it underneath here, right? Let's just say there, something like that. It looks a little bit better, right? So this point here is the center of the circle. Let's just call that B, and then it touches this point here. So not this point here, but this point here, right? Let's just call that A on the circumference then of the circular path, right? And let me just quickly get rid of that point there, hopefully without deleting the full circle. I'll give it a go. There we go. Perfect. Okay. What else do I need here then? So this here is our particle, right? So we have a weight force here acting vertically downwards. We have a weight force acting vertically downwards here, like so. Something like this, right? Clearly, this should just be a straight line. You get what I'm trying to draw here. And where it cuts through here, the circular path, this will be the lowest point then, okay, of the path. So I'll denote that here as well with another kind of dot, like that. So I've got B here, the center of the circle. What I also have here is a tension, right? We have a tension in the rod. So I'll denote that here. Like that. So I've got the tension here. We have the weight force acting vertically downwards. So if the mass is 0.2 kg, then the weight force here is 0.2 g, right? I've got 0.2 g, just like that. And then I've got the length here of the rod. So that's 0.5 meters. So I'll also add that to our diagram. Something like that. And I think at this point here, that will do. As you can see, my art skills here are certainly not the best, but it doesn't really matter too much, right? As long as we can basically make out what's happening with this problem, okay? So first things first then, what I'm going to do here is let the speed of the particle at the lowest point be v meters per second, okay? And for the next point here, I've already kind of done that with my diagram, but I'll let the tension in the rod be T, right? So let's just mention that here then. So we let the speed here. So let the speed of the particle at the speed of the particle at the lowest point B, we're going to let that be V meters per second, just like that. And the tension in the rod will be T, okay, or T newtons here. And the tension in the rod be T newtons. Okay, perfect. Again, a little bit more kind of like yapping here is required because what I now need to state here is that the lowest point of the circle is the zero level for potential energy, right? Because we do need to take into account here potential and kinetic energy. So let's make another point here. Again, it is important that we do state these kind of, facts here, right? So the lowest point of the circle is a zero level for potential energy. Okay, and it is important that we do state this here. It's a zero level for potential energy. So where do we go from here then? So at the lowest point, the particle will have fallen a distance of 0.5 meters, right? Because the radius here is 0.5 meters. So in that case then, once it gets to this point here, the lowest point on the circle, then it's fallen a distance of 0.5 meters. So what that means here then is the potential energy loss, so just kind of denote this here as P dot E, potential energy loss then, that is equal to, so what I get here is 0.2 times G times by a distance, right, that it's kind of dropped here, or it's fallen. So I get 0.2 times G times 0.5. And let's also just consider here then the kinetic energy gained. So the kinetic energy gained here, what will that be? So for the kinetic energy gained here, that's going to be a half mv squared, right? So I've got a half here times by the mass of the particle, which is 0.2, as we're told here in the question. Times that by 0.2, and then we times that by v squared. Now, at this point here, we don't know what v is, right? We just times that by v squared. Perfect. Okay, where v here is the speed of the particle at the lowest point. And at this point here, what we can now do then is just use the conservation of energy, right? So what that means then is the potential energy lost is equal to the kinetic energy gained. So let's just make a quick note here then. So using the conservation of energy, here, write this down. As we just said then, what that means here is the potential energy loss is equal to the kinetic energy gained. P dot E lost is equal to K dot E gained. I mean, you don't need to really kind of bother writing this down here, but I'm just going to do it anyway, just for the sake of completeness and just to show all of my steps here. What does that mean here then? So what that means here then is 0.2 times G times 0.5 is equal to a half times 0.2 times V squared. So 0.2 times G times 0.5 is equal to a half times 0.2 times V squared. If we just simplify this here then, what do we get? So 0.2 times 0.5, that's 0.1. I've got 0.1 G. 0.1 G is equal to, again, 0.5 times 0.2 here is 0.1, so 0.1 V squared. And clearly, if I just divide both sides by 0.1 here, what I've got then is V squared is equal to G. And then finally, if I just want the speed of the particle as it passes through the lowest point of the path here, then in that case, V here is just simply the square root of G, right? So V is equal to the square root of g here. So root g meters per second. If you want to, you can give this as a decimal equivalent here. As a decimal then to two significant figures here. What we get then is 3.1 meters per second. Perfect. Okay. And I've just noticed that I never did note that this was for part A, right? But this here was for part A. So for part B then, let's just quickly box this off here. Something like this here. Should be enough room, I hope. So for part B then, let's just do that over here in the bottom right corner. So we want to find then the tension in the rod at this point, okay? So at the lowest point then, the force towards the center of the circle will just be given then by resolving vertically, okay? So let's just resolve here vertically, taking upwards as positive then, okay? So what do we have here then? So in this case here, we do need to account for vertical acceleration, right? The vertical acceleration here will be A is equal to V squared over R, okay? So what that means is we do need to use Newton's second law here. So F then is going to be T minus the force acting downwards, which is 0.2 G. We get T minus 0.2 G is equal to then the mass times the acceleration. So the mass here is going to be 0.2, right? So I get 0.2 times by the acceleration here. So V then is root G. So V squared is G, as we've got it here. So I've got 0.2 times A here, the acceleration, which is going to be G over R. And R here is 0.5. So for this question here, I'll just denote it here just so I don't confuse myself. A is equal to G over 0.5, right? Just like that. So then I get 0.2 times by this here. So G all over 0.5, which is just the same then as 0.4 G here. I've got T minus 0.2 G is equal to 0.4 G. And then finally, right, if we just want T here, that's what we're looking for, the tension in the rod at this point here. Then all I need to do here, right, is just add 0.2 G to both sides. So therefore, T then is equal to 0.6 G. Perfect. Beautiful. Okay. And there we go then. If you want to, you can give this a decimal as well. So that would be 0.6 G newtons there. Or you could write this here as T is equal to, what is that? So put that into your calculator, right? And this is 5.88 newtons there. Again, perfect. Okay. Good stuff. So there we have it then. So that gives us the solution here to the one practice question for this video. And that brings us to the end then of this video here on objects moving in vertical circles.